Greetings. Welcome to the Evidence and Reasons for the Christian Faith video channel. I'm Salvador Cordova. It says in Proverbs 25:2, it's the glory of God to conceal a matter. It is the glory of kings to search out a matter. One reason that it's difficult to help inspire other people into the Christian faith is God himself does not make it himself as obvious as the air we breathe. It said in the New Testament that Jesus revealed himself first to the women in the garden, and then the women went to the apostles and they thought the women were just giving idle tales. And how much more then is it difficult for us in the 21st century to believe these aren't idle tales? And I just try to point that out. That's an interesting reaction. Then Jesus revealed himself to the apostles, then to 500 chosen witnesses. And the word for witness in the New Testament is martyr. So you know that there's a responsibility that comes to witnessing the Lord and witnessing his miracles. And last but not least was the Apostle Paul. So it says in the Bible, few are those who find the way that leads to life. And the kingdom of heaven is like a treasure hidden in a field. That means God doesn't hand you the evidence on a silver platter. He has left clues for his existence in the historical record, in nature, and you have to think about it and explore it. And occasionally, God will work in people's lives, miracles of healing, and there are people on this channel that have witnessed it and experienced it themselves, and that's one of the reasons they have remained in the Christian faith or become Christians. Today we'll be talking about things related to the Big Bang. If the Big Bang has problems, it may or may not support the idea of a miraculous creation, but let's just explore some of this. And this is just going to be an afternoon nerd session. There's enough complexity and difficulty in understanding cosmology that just relates to basic electrical engineering, quantum mechanics, photonics, you name it. I have in the last in the last month, I have 5 science degrees. I'm now considering pursuing a PhD, which would be a 6th science degree, and it's going to be brutal. And I have a lot to weigh whether I will do that. And part of my inspiration for that is people like Ben Rex here, and others who said, well, they've been watching my channel and inspired them to apply to graduate school. I'm just like, well, I guess that puts the fire under my feet. I shouldn't, be sitting around either. I should be trying to advance my knowledge. So Ben Rex, just feel free to share about who you are and whatever you feel comfortable sharing. I do try to protect the anonymity of people here, and and so just whatever you feel like sharing and about yourself and what you hope to talk about today.
Yeah. Hi, I'm Ben Rex 777, and I'm from Switzerland. Young Christian guy who I'm agnostic on the edge of the Earth and universe, just because no theory makes sense in my opinion, and I don't really know what. Oh yeah, I studied electrical engineering. I have a bachelor degree in it, and I applied for getting the master's in photonics, but the school didn't give a reply yet. And yeah, it's like Sal said, communities like this here are part of the reason why I thought about going to school again. And yeah, I don't know what else to say.
Well, well, that's great. We'll just get to know each other. I have, to me, at the time, my most important degree was in electrical engineering. That only got superseded by my physics degree, grad school. But the electrical engineering discipline, at least at George Mason University, was the hardest curriculum. It was brutal. And of course, looking back now, that was not as bad as graduate school, especially classical mechanics. But that's why I have a connection to you, Ben Rex, because I was trying to build toys and I was learning how to build circuits, and I still remember building my first electro-optic system, where I was able to make is like a small dirigible, and I used a flashlight to make the thing go up and down. I connected it to a transistor. Yeah, I connected a cadmium disulfide sensor to a transistor, and I thought that was a great accomplishment to a bipolar junction transistor. So every now and then when I see electrical engineering stuff, I said, I think of you, because that's a part of my life that I don't get to exercise a lot.
I think our electrical engineering degrees were quite different, because some things you say are a bit foreign to me, and other things you said which you didn't know, I was like, isn't that 101? And so it's a bit it's a bit different, but yeah, but every school is different, and I went to a university of applied science and on a different continent, so perhaps that also contributes to it.
Yeah, ours was very theoretical, and a lot of it, and I'll say this from my experience in the USA, a lot of the electrical engineering that they teach in college at university level, they graduate, they hardly ever use it in on the job. For example, they teach you how to build circuits and all. You get on the job, a lot in the defense industry, it's like, oh, just tell us what your requirements are. We'll send it off to the, we'll send it off to the guys that'll make the chip for you, and they'll just charge you a bundle of money, but then you don't worry about it. So it's like, okay, if you want this filter that has these characteristics, just tell us your specifications and you contract it out.
For us, creating those chips is like I always struggle with certain specific words. No, it was like just an advanced course, not the basic ones we learn. Like we start out with the basics, like math, physics, programming, and electronics, or just electrical stuff, or electrical specific physics. And then that's the base layer. Then we have obviously projects and lab works and stuff like this. And afterwards, we can choose which direction we want to focus in. And basically, we have two main focus groups. We call it thin currents and fat currents. That's translated. It's more of a joking way. But there in the if we want big currents, then we basically go into motors and power electronics. And if you want to have small currents, then it's more like communication theory and by drawing electrical circuits, how those silicon wafers are done and stuff like this. So those are just a specialization, but we can basically choose whatever we want. So I took a control theory from the large current specialization, and I didn't take the communication theory, or at least not the more advanced stuff of it. So yeah, we can mix in however way we want.
Yes, yes. I didn't do very well in control theory. So today we're just going to talk about photonics, and no, it's going to be a free-forming thing. At issue is I put out a paper, and I'm in communication. I'm going to try to be in communication with some people that the redshift of the Big Bang has been claimed to be caused to be Doppler-like. I mean, formally it's not Doppler. There's some subtleties with expanding space that are not really like the Doppler of, sound effects. But Crawford's paper and then others have indicated that there was just kind of a circular reasoning and just picking and choosing of what data points look like time dilation. If you look at the majority of the data points of supernova at various redshifts, they don't show any time dilation. So these studies that are promoted on the internet and even in especially in professional literature, that the redshift was definitely confirmed as expansion of space, that is not true. There have been now more experiments that have shown varieties of redshift can be induced through interaction with electrons. The one that won the Nobel Prize is Compton Scattering by Sir Arthur Hawley Compton, where an interaction of a photon with an electron will cause a redshift. But that can't possibly be the explanation for why the redshift from stars is redshifted. But it does show that you can change, that electron interactions can change the wavelength, and that was the start. So there are other forms of interactions that we have to consider. And this is where it starts to get down into some real electrical engineering, just like talking about the different kinds of electromagnetic waves, from like radio waves to, I guess, infrared, then visible light, ultraviolet, X-rays, gamma rays, etc. And so we also, this started because Ben Rex is very interested in the variable speed of light theory. I said, we'll do a show on that. But then also the paper I was reading that talked about a different kind of electron interaction with photons that can possibly create redshift. Now that was a theoretical paper, but I've been combing the literature, and there's been more and more both lab experiments and then, experiments within our solar system, like where we took the Pioneer 6 radio waves. As the radio waves travel through the electron plasmas of the sun, it got redshifted. And then we're seeing some of this also in the atmospheric studies. So this is going to be very problematic for the Big Bang theory, because if you completely say all of the redshift is due to cosmological, and you fail to account for the effect of electron interactions with that, this is really bad, because that's something you need to fix in your model, first of all. Let's just say it's true. You need to add some correction factors that aren't there. The worst case is that it can account, the plasmas alone can account for it. Now, at my school, there were 3 professors, 3.5 professors. What I mean, there are 3 professors definitely against the Big Bang, and one of them was kind of halfway, kind of undecided. And I have links in the video description of their works that are by Menas Kafatos and Sisir Roy, and they're insane papers. Okay, so there's still a variety of attempts to explain the redshift. So why don't I just put I'll put something up on the screen here, and we could talk about. So we're just going to learn some of the terminology here. So Ben Rex, I could just read this. And so you said you're looking to apply to study photonics. Is that correct?
Yes, that's correct. And
All right.
I also, at my school in the first semester, we had a physics course about temperature and radiation. And there it went into basically the whole range of it, the physics. And so in the paper where which Sal was talking about here, there a lot of things looked familiar to me, like those complicated math formulas. I thought like, yeah, that's just the shape of the antenna, and it's repeated again and again. And Sal was every time he was wondering again what it means, and that was funny for me and stuff like this. So I already know a bit about it, but yeah, obviously it was just one course, but with a good teacher.
So, Andrew here says nobody thinks all redshift is due to cosmic expansion. That's fair. I was pointing out that they're not adding a correction factor for the effect of plasma. And if they're not doing that, and we find out that the plasmas can change the redshift, this is really bad. I mean, especially if it's significant. So anyway, I'm just going to read this for the sake of the audience here. Is that all right with you, Ben Rex?
Yes.
Because I'm embarrassed to say I actually worked in the photonics field briefly, and I never got a definition. So photonics is the physical science and the application of light photon generation, detection, and manipulation through emission, transmission, modulation, signal processing, switching, amplification, and sensing. Though covering all light's technical applications over the whole spectrum, most photonic applications are in the range of visible and near-infrared light. The term photonics developed as an outgrowth of the first practical semiconductor light emitters invented in the early 1960s, and optical fibers were developed in the 1970s. And this is a huge field. I'm just going to...
Yeah, in Switzerland, there are several different schools about, which teach that. They were in different universities. They have 4 areas of focus. Like the one I go to is about lasers, like developing lasers and obviously doing research on them. Then there is thin film processing. I think that's the one I know least about. Then there is sensors like, I don't know, lidar and uh, just stuff which is probably used for geology measurements and I don't know whatever else. And then the last branch is medicine or medical devices like X-ray machines and whatever else there is. So those are the 4 things which photonics is about, at least in Swiss universities. And each school obviously specializes in their own field. For example, Bern is in Switzerland where universities are good with medicine. And because of that, the photonics school there also specializes in medical devices. Or, yeah, that's a bit of an overview.
Oh, thank you. Thank you. And by the way, let me know if I'm keeping you up too late. And
No problem. It's still early.
So this is really interesting here, just all the applications of photonics. And I got to brag about this. It says here, a sea mouse showing colorful spines, a remarkable example of photonic engineering by a living organism. I just like the way that they're pointing out there's photonic engineering in life. That's why, I mean, am I fair to presume that you're friendly toward intelligent design? That God had done something to create life?
I grew up with the background of young Earth creationism, and I left. Basically, I left that being convinced that's true because I didn't see any convincing models about stuff. But it would definitely make my theology easier if it was true, and it was also be like I would like it to be true, but currently I don't know. And
Okay.
but the young Earth creationists asked a lot of questions which the old Earth people in general need to answer, and I haven't heard answers. So I'm also not old Earth. I would say neither of them is convincing for me at the moment. So I'm just agnostic.
Okay. So we'll just push through this. I just need to pounce on something here. I'm not talking about reddening due to dust and gas. So Andrew Cummings saying that, and I do feel I need to acknowledge what's in the chat here, because I need to just cut this off before I feel my point is going to be totally misrepresented and people think, I'm going down a certain path that I'm not. Sorry about that. Now I got to tell you something. Well, I've covered the biology stuff and here, and for myself as an engineer, I'm more and more convinced there had to be a miracle there for at least the first life, and then also what we call eukaryotic evolution. The engineering is just too sophisticated to be the product of random mutation and natural selection, and I've defended that here. But I got to show you something here. There is one part of photonics called polaritonics, and I only just called this up yesterday to look at this Wikipedia page, which differs from photonics in that the fundamental information carrier is a polariton. Polaritons are a mixture of photons and phonons and operate in the range of frequencies from 300 gigahertz to approximately 10 terahertz. And the reason I'm pointing that out, you probably saw the list of Quasi. You probably saw the show on quasi particles, heavy electron quasi particles, and I just thought I'd share this with you today. And there's Justin. Greetings, Justin Witzit. Thank you very much. Okay, so a couple weeks ago we talked about heavy electron quasi-particles. And here's a list of various quasi-particles.
Yeah, by the way, the electron hole really helped me understand what a quasi-particle is.
Yeah, isn't that crazy? See, why don't they come up with a more exotic name for the electron hole? Because you have all these other quasi-particles. Now, the exciton, it is a bound state of an electron plus a hole. This has been discovered in biology in plants. So I don't know if if in his image, Emery Moyna is here. He's our resident plant biologist. But in my biochemistry
By the
text.
way, so, I want to say something to Emery. I'm reading a book about plant physiology, and it was released in 1956, so it's quite old. But yeah, it's very interesting. It's written. It's a similar depth of like the book that Sal published in, also by Springer Nature, and 1,000 pages long, and each chapter is by a different scientist, and like half the chapters are in English and half the chapters are in German, and one chapter is in French.
Wow.
I'm not there yet, so I don't know if my French can hold up, but I doubt it, but it might. And yeah, I'm halfway through it, and I'm considering buying the other 19 books because it's pretty interesting.
I mean, wow. See, you have very diverse interests, which a lot of the people in the side chat are just like you and me. We have diverse interests. before I forget, because many of our Christian brothers are here, I'm just going to offer a prayer. Lord Jesus, I dedicate this stream and this time of fellowship to your glory. In Jesus' name, I thank you for each and every one here that is a believing brother or sister. Thank you, Lord, and help this show to be a blessing to those live and those who watch by recording. In Jesus' name, amen. I just, I see my friends here who are my dear Christian brothers and sisters, and like Emery, Patrick, and Mr. Jetty. So, and Janet, and if I miss someone, I'm sorry. Oh boy, yes, pardon my French. So it's been great having these shows in the afternoon. Some of you know, I've been working from home for the last few weeks, but I will have to get out of the house eventually. But I'm just amazed at all these quasi-particles. Majorna fermion, I heard about that. This is incredible. Look at all these. And then, okay, the polariton. And the list keeps growing. So, we learn in school the electron, the neutron, the proton, and now we have all these quasi-particles. So I just thought I just wanted to share that with everybody. So now we can get to some of the topics now that we know a little bit of, just got acquainted. So I'm going to cover Compton scattering. And I could show that this is kind of well known. I mean, no, it is not kind of, it is very well known. It won the Nobel Prize. When see if they have it here, if there's a diagram. So if you have a high energy photon and it strikes an electron, the photon will be redshifted. And so this is an example where there's an interaction of a photon with an electron, and its wavelength gets lengthened. So we call that redshifting. A paper in 1968 said, well, there's no way to tell the difference between a Doppler redshift and a Compton redshift. Well, this can't be the explanation for why the light from distant stars is redshifted, because for the Compton scattering to work well, it has to be at an angle. Oddly enough, if it's straight on, it doesn't redshift, which I don't know why it does that. But at least in principle, it shows that what has to happen is there has to be a transfer of energy from the photon into the electron. And we're trying to figure out, the plasma cosmologists are looking at that. So I learned a new term. Well, I knew this term before, but it's just been so long. It's what they call the Compton wavelength. So I'm just going through some terms here.
Yeah, those are the things I'm not really familiar with.
Okay, so
Yeah.
go on.
No, I was just thinking if I know those two formulas which are currently present on the screen, but probably
Actually,
I've seen them. But
yeah, they're not used a lot. I'll show you probably one. I'll show you probably the fundamental one. Planck-Einstein relation. This is Nobel Prize winning stuff. Let's see. I think Einstein won the Nobel Prize for this one. Very simple formula. Energy equals h nu.
Yeah, I've
and
seen that.
Yeah, a professor once said, okay, this is probably if we do photonics, this is probably one of the most important formulas. A professor of mine said, how do you know you're dealing with quantum mechanics? And this is like the opening day of quantum mechanics. And everyone kind of said this or that. He said, okay, anytime you see H, you're definitely doing quantum mechanics. It's a quantum mechanical phenomenon. So H is Planck's constant, and nu is the frequency. That looks like a V. It's the Greek letter nu. And then the energy. So the energy can be expressed in joules or watt seconds, but typically the unit they use is the electron volt. So let's look at electron volt. The electron volt, and this is, by the way, I hope I'm not terribly boring you, but this is just kind of good review for me. So an electron volt is 1.602 whatever times 10 to the minus 19 joules. And a joule is 1 watt second. So when we calculate that Planck-Einstein, that Planck relation, some people call it the Planck-Einstein relation because Einstein won the Nobel Prize for this relation, but they call it the Planck relation. It's often expressed in electron volts. If you had any comments.
No, I don't.
Okay, so part of this is really for our viewers. I know this is probably too trivial for you, but
It's already been like I worked for 2.5 years, then half a year unemployed, plus around 3 years where it's back. So it's like 6 years ago. So it's not. It is repetition, and sometimes I can have it at school. And when I look at the Wikipedia page, I think, what kind of math are they using here? Because my school is more, or my entire career was more focused on the practical application. So they didn't go at it from the theoretical math side, but from already simplified stuff sometimes. So yeah, it might sometimes it's new or unknown for me, even though it's basics.
yeah.
Just yeah.
And I think the way we have like, okay, let's see, look, radian frequency. Let's look at the radian frequency. Angular, so frequency is usually, okay. So we have also angular frequency. And it gets a little confusing because sometimes in the literature, it'll be, frequency like hertz, I think. And then other times you'll see the angular frequency. So let me just look at this. Because we see lots of omegas.
Oh, yeah, omegas is.
Okay, see, this is what's a little obnoxious. Is
That's basics for me.
see, they have F, but in other times they call it nu. So, all right. Okay, so just under this, because actually I was reading through the paper and just like, okay, I need to get all this because there is these conversions and I can just be kind of confused. So
I have a question, Sal. How much of the SE units did you use at school? Standard, I don't know the name.
Oh, for physics, it's almost always in SI units.
Yeah, but why did you struggle with watts divided by meters times nanometers? That's like
I was
all
just,
SE units, and it's yeah. You were
oh no, that's a good question. I'm just like, why isn't it like meters cubed times n? I just never saw that before. In what they call it, it was irradiance or something. So yeah, I'm just like, you have m squared times nm. I would think that's nm cubed. That's why I was confused. I've never seen that. I would have just thought they'd say cubic meters or nanocubic meters. So that's why I was confused.
Okay.
Yeah, no, it had nothing to do because I was not going metric. Okay, so yeah, Mr. Jetty said this things go round and round. So now I'm going to just totally switch gears and now go into nerd mode. But I really was thinking about this because I was misreading. You know how it is sometimes you're so used to reading stuff at the high level, you forget kind of the basics, and I've sort of done that. So let me show you some interesting, I put it in the video description here, and let me just take this down for the moment. Hang on. I'm getting too many windows open. So if you have any comments while I try to fish up the paper I'm looking for, and I'm going to present it.
No, I don't have any comments.
Okay. So let me see some of the experiments. And I'm going to present it. Ooh. Okay. So let me see some of the experiments. And I'm going to present it. Ooh. Okay. So let me see some of the experiments. And I'm going to present it. Ooh. Okay. So let me see some of the experiments. Sorry about that. I was playing my own video and you're getting feedback.
Yeah,
So, and I was
sorry
panicking a little.
Sorry about not being good at filling time.
Oh, no, that's all
I
right.
don't know what to say.
Okay, so now I'm just going to give you some of the alternate. I'm just going to read the abstracts of some of these alternate redshift ideas. Okay, so when people wonder why I'm very how I got inclined to reject the Big Bang, it was professors at my school. I know that sounds just like, what school did you go to? I went to two mainstream schools, but they had respected dissenters that were very accomplished professors. So I'm just going to read the abstract here. I'm not saying that that I agree with it, but just so you know, kind of like what they taught in my school. So we're just going to totally shift gears here. We were doing some really basic stuff, and now we're going to just see what other people say. And I'm not saying that any of this makes sense to me. So Menas Kafatos, Sisir Roy, and Malabika Roay were professors at my undergrad alma mater, George Mason University. And so obviously, if you see professors in your school saying the Big Bang's wrong, it has an influence. It has an influence. It had an influence on me. So he said, okay, theories of fundamental physics as well as cosmology must ultimately not only account for the structure and evolution of the universe and the physics of fundamental interactions, but also lead to an understanding of why this particular universe follows the physics that it does. Such theories must ultimately lead to an understanding of the values of the fundamental constants themselves. However, all such efforts have failed, leaving fundamental constants outside of any physical theories. In this paper, we take a different approach than the usual evolutionary picture, where the physics itself is assumed invariant. We study numerical relations among the constants from the relationships proposed by Weinberg. We have shown that they turn out to be equivalent relations found by Dirac. Then a new scaling hypothesis relating the speed of light c and the scale of the universe is explored. So that wasn't too bad.
Is it? I always thought the reason why the physics are how they are is in the realm of philosophy and not in the realm of physics. And here they say that physics and a good physics theory also explains why the physics are how they are. Um, is it in the realm of physics or is it in the realm of philosophy?
Yeah, and I don't know. I think that's above my pay grade at this point. But I just showing those are the three that were at my school. And then I'll give you one of Kafat, his other one. This was about the redshift. So let me see if I could put this on. This one's just crazy. This is while he was at Chapman University. It says here, Einstein's refinement of Newtonian gravitation repeated for general relativity by quantum cosmology requires inflationary models of the universe to be critically reevaluated. The Hubble redshift is shown not to result from Doppler velocity, but anisotropic coupling to vacuum zero-point fluctuations through harmonic structure described in terms of the Wheeler-Feynman absorber theory of radiation in the context of the Dirac vacuum in compactification dynamics. The quantum gravity of the co-moving hyperstructure of a universe topologically both open and closed like a Klein bottle also implies that frequency shift in photon propagation over cosmological distances is an inherent part of the spin exchange process, removing the ad hoc criticisms of the well-known Vigier theory of tired light. I didn't understand a thing that said, and he's a professor at my school. Just, okay. So we went from something really simple earlier to this, and that was still too much of a gear change. He was criticizing the Big Bang Theory here and invoking what quote unquote tired light, but a different mechanism than gas and dust. Are you familiar with the tired light model?
No, not at all.
Okay, so the Big Bang at its core is that we've seen that the farther out we look, as we look at objects like galaxies or whatever, or we're definitely see, as we look out in space, we see some galaxies that are what they call redshifted.
Yes.
And the question is, you know, the first inclination was this means that the galaxies are moving away from us. That was among a lot of people. Hubble himself, who discovered it, was, I think, as far as I could tell, was still ambivalent. He was not completely comfortable. One of his pupils was Halton Arp, who vigorously opposed that interpretation. So one of the first alternative things saying, rather than moving away from us, is tired light, or it's gas and dust, but it wasn't very well developed. It was like in 1929. And rightly so, they said, well, you know, there would be problems if it's gas and dust. Later on, there have been various other explanations for what may cause that redshift. If the redshift is due to something that's happening to the major component of the redshift. There are other things like you know, gravity can do that, and even just like mechanical actual velocity, like the galaxy spin or whatever. But the major explanation has been that the stars are moving away from us, what they call expansion. It's the more formal term. But if we find out, I'm sorry.
All the way until the expansion, I knew I had at university I had a course about cosmology, and they basically just did the history of what people found out from way in the past until basically infinite expansion, or the expansion theory. But they didn't go too in depth, and they had two teachers. One was astronomist, and the other one was like the head of the religion department. And they not only looked at the discovery, but also at what kind of influence that had on the worldview into that direction. But it was like an elective course, so it wasn't too in-depth, and the two teachers weren't much into agreement with each other.
Wow.
Because of their different background.
Right.
But yeah. So I know let's just say I'm on Mount Stupid when it comes to astronomy. I know the basic model, and um, I know enough that I start to get an understanding of it, but of all the controversies behind it, I vaguely heard about them.
Yeah. So, and then part of the reason I'm going over this is also for the audience in case they're curious. So, but that whole thing about the space expanding is based on the uh, interpretation that the redshift means that it's moving away. You know, and some people will be formalists. You know, at first it was just moving away. Then they started to add these things like what they call the Friedman, Robertson, Walker, Lamart solution to the Einstein field equations. So you have kind of a different language, but kind of like at a more simple kind of, you know, layman term, it's moving away. And so, but we don't have independent evidence that it's actually moving away. We just have the light that's redshifted. And so I've been covering on my channel why some people have objected to that. So what would happen if we find out that light photons passing through electron, what they call free electron rich plasmas, can cause the redshift? Now we know that when it strikes the electron, if the frequency is high enough, which means the wavelength is short enough, it's shorter than the Compton wavelength, it'll get redshifted, but the problem is it'll scatter. You know, what you want is the light to, when it's coming from the star, it's going toward our telescopes or our eyes, and it's not going to be directed, you know, away from its incident line, if you get what I mean.
Think so.
It'll have a straight path to us. The Compton scattering will make it go, you know, all sorts of directions rather than toward us, but it will redshift it. So someone had said this could be Compton scattering, then people figured out right away, it's like, no, that's not going to work, because to get that redshift, it has to be bounced off. The photon has to bounce off at an angle, so that failed. But then there've been other experiments that have suggested this. One of the most, are you familiar? You know, I sort of know this about linearly polarized light and
Yes,
circularly. Okay, okay,
I know
great.
that.
Okay, excellent. So I've been digging through the archives, and there is this polarization thing. I'm gonna just put it out here. And this is in the video description. And this is kind of killer right here. Now they're reluctant, the authors are reluctant to say, well, this is caused by plasmas. And I'm like, well, you know, if you're willing to be a little bit open, here's what I found. It says here, what's the title of the paper? I'm sorry, hang on. The optical polarization of high and intermediate redshift radio galaxies. The optical polarization of high and intermediate redshift radio galaxies. Apparently, this is where the photonics would come in. I think there's situations where polarized light can penetrate a plasma better. And therefore the unpolarized light is attenuated. So what?
I don't really know anything about that. But I do know that, for example, there are sunglasses which are polarized, like linearly polarized, and they are that way because when the sun hits the water surface of the ocean or whatever, then it gets polarized by reflecting from the water surface, and by polarizing the sunglasses, then you can basically filter out that specific light. And that's just an additional protection of the eye.
Yeah,
So I don't know about going through gases or plasma, about polarization, but that's
okay.
what I had to think about.
So this optical polarization of high and intermediate, so the farther out galaxies, the more redshifted ones, the light is also more polarized. And I didn't see that in any of my cosmology classes that we would expect. That is not a prediction of expanding space, that it induces more polarization with increasing redshift. That would be consistent, though, with going through electron rich, free electron rich plasmas. And it would be correlated. It's correlated with distance. This was what I was digging up. And I have to admit, I had some sleepless nights thinking on this. This is not, this, this is one important data point. One important data point. So we could just file that away. And the other fact is that the redshift, it's kind of complicated. You know, the faster things are moving apart from each other, you get what they call time dilation. And so something looks like it's going in slow motion or fast motion, something like that. There is a relationship there. And if space is expanding and these things are moving away, we would expect to detect time dilation. And it should be consistent with redshift. What we found is we found a lot of counterexamples where something wasn't time dilating when it should have. We have found that in gamma ray bursts and quasars and also lots of supernova. So all these supernova studies that said we found time dilation, they actually did circular reasoning and picked only the data points that would suggest it and ignored the majority of data points that said it's not.
What
And
do you
that's a
mean with
2008.
time dilation?
I'm sorry.
What do you mean with time dilation?
Okay, so the clock will slow down. The clock. So if you experience acceleration,
Yes.
so like they actually did this. Variety of experiments we could do. We could get a very precise cesium beam atomic clock. So get your atomic clock, and then put it on a rocket ship and send it, and get it to accelerate very, very fast. The clock will tick slower than our earthbound clocks.
So pulsars would have a known way of blinking, for example, and that can be compared to the redshift, or what do you mean exactly? Or
Um,
how do you know? How do we know about time dilation of objects which are far away?
Well, see, that's exactly the problem. If you don't know if you happen to have the clock with, let's say you have two clocks and then you can send one out to space, then you know how fast it really is ticking. See, that's your critical thinking skills right there. How do you know inherently what the clock rate is of an object out there? You're guessing. And so what we do is we try to look at objects close to us and kind of guess uh, how fast they tick. I mean, this is a gross simplification. If we look at the ones far away and they tick at a slower rate, then we would presume that's time dilation. So one of the clocks is a supernova, what they call the light curve, how long it takes to explode to reach the peak of brightness and then die away. So we kind of average how fast this happens close to us, and then we average how fast it happens to objects far away. And Crawford and three independent papers arrived at the conclusion we have a lot of supernova far away that don't show any evidence of slowing down. The only way you can get the claim that it slows down is to cherry pick your data points, and that's what had been done. I'm not accusing anyone of lying, but what they had done is introduce a subtle circular reasoning where they ended up filtering out the points that they really wanted because they're assuming the very thing that they're trying to prove. And there was that graph. I should show it because it's really embarrassing. Rather than talking about it, I'll show the graph because it's really kind of picture's worth 1,000 words. And let me see, Crawford 2017. Let me bring this up. So we have the circular, we have the polarization correlated with redshift, and then I'll show the absence, what they would call the absence of time dilation. And I'm going to just put this. So this is a 2018 paper that's just kind of a revision of an earlier one. And I'd probably want to contact Dr. Crawford himself. But I'll show you what I mean by cherry picking. So Andrew Cumming keeps insisting they've proven that there's time dilation. And I'll try to explain this graph here. There are all these various, all the dots are like supernova in the various frequencies. And okay, as it gets more redshifted, we should start to see more time dilation here. We should see more supernova along this. You see that line there?
Yes, I see it.
Whereas most of the points are not on that line. So why is it that one study reported time dilation and another? Well, all you have to do is just cherry pick all the points you want to convince yourself of time dilation. Now, this wasn't done consciously. What Crawford did a very good job of is he looked at their materials and methods and realized, oh my, they're doing circular reasoning. They're assuming the very thing that they're trying to prove. So hence, they ended up rejecting all these data points based on their own methodology. It was circular reasoning. It was cherry picking because they're reasoning in circles. So it's not deliberate, but at some point you have to just call it out. Because when I saw this, I said, it's so obvious. And so many people on the internet especially, but even professionally, they keep citing the studies that just pick points along this line. And they forget all the ones, they don't like to cite this one. And some researchers have noted that. And I said, there's been further studies that we have things like quasars and gamma ray bursts that don't show it, that have kind of the same profile here. And so now it's wide open for the redshift to be interpreted as something else than cosmic expansion. And if I may point out, we don't have any proof on Earth that space is expanding, or even in the solar system. And people say, well, it's just so minute, you can't detect it. And I'm just like, well, okay, then you should say, I don't know. You can't, you can't insist that it's fact. There's no independent verification that the space is expanding, no independent verification that there's time dilation. It's just an assumption at this point. And there's a saying by Huxley. He said, the tragedy of science, an ugly fact can destroy a beautiful hypothesis. And I think evidence of the plasma contribution to the redshift is that ugly fact. The whole band could fall apart on it. That's why I'm interested in photonics now. That's why I'm really interested in photonics. And this is right down our alley as fellow electrical engineers, because we could study whether the frequency shifts in radio waves passing through the ionosphere or through the coronas of the sun. And there have been studies to that effect. So let me cite that. So we know we have the cosmic expansion does not predict the correlation of polarization to redshift, but plasma would do that. Plasma would do that.
Is plasma spread all over the universe, or is it? I don't really know the matter of the vacuum between the interstellar and intergalactic space. So is that plasma, or what
It,
is the
it's
material there?
okay. So there are various ways we'd have to extrapolate. So just to be fair, we haven't sent spaceships out that far to measure. Okay, so we have to make some guesses based on, I guess, what we can measure with our space probes or whatever, or some other method. But there are what they call free electron plasmas between the stars and the galaxies, and we have an estimate of the density.
What
So,
is
so
a
it's
what is a free electron plasma?
okay. First, I've only heard that term recently, so I'm going to guess. So usually you have an electron with a proton, and that makes an atom, and then the atoms make
Yes.
molecules. Sometimes you could just have electrons that are not tied to any atomic nuclei, and I think that's what a free electron is. I'm pretty sure.
So,
Yeah.
so free electron plasma is basically just a cloud of electrons, or?
Yeah, and I don't know where the protons are. So this is why I want to go to school, because then I have access to a professor. I'll say, what happened to the protons? Now I did take plasma. I took plasma physics, and we were just focusing on the electrons. I never bothered to ask them what happened to the protons. I know, just I was just trying to solve all these electromagnetic questions,
Yeah.
and Maxwell's equations were just miserable. And he's saying, okay, what happens when the electron goes through this magnetic field? I'm just like, I don't know, sir. I
We
never.
never had Maxwell, or we saw the formulas, but we never had to, and we had a basic description of them, like the teacher quickly explained it to us, but we never had to calculate with it.
Oh yeah, that was plasma physics, and there's something called the magnetohydrodynamic model of plasmas, where they took something that was similar in hydrodynamics of water, and you had to apply it. That was a question on the exam. I totally just gave up at that point on that question. I got to be in the class, and I was happy, because that was also very. My eyes were rolling every day that I was in lecture, and I go to my fellow students. I said, I don't think I understood anything he said after the first 3 minutes. And they'd say, yeah, we were in the same boat.
Yeah, I
Okay,
never
so
had that in the physics classes, but I had it in my Linux class where I had to learn Linux, and I was like, yeah, I passed, but I didn't understand it.
yeah, so you know what I mean. Okay, so I talked about the polarization, and then now I'm going to show there is this paper where they studied the redshifts of. Okay, so we have a space probe that was out there, and the Earth orbits the sun, so you're in a position when the space probe is going one way, the Earth is rotating around the sun. You'll have a chance to actually observe the radio signals coming from the space probe as it passes through the solar corona. And so this one has the redshift anomaly of 292 megahertz radio signal emitted by Pioneer 6 space probe as multiple interactions with photoionized electrons in the solar corona. So this is an example where we got a redshift just because a radio signal is going through a whole bunch of electrons. And this was a brutal paper. This was like, I think this would take me 2 years of study to get through it, because it was just brutally detailed. And this is electrical engineering and electromagnetic physics, just awesome. And he was so this paper's in the video description, but I'm like, okay, so this could be empirical proof that an free electron plasma can cause redshifts, and then it would be consistent with the polarization and redshifts. and this just goes on. I'm only through half the paper. I'm just showing this off. If anyone wants to criticize this, here it is. You know, you can. This is what it would take, and you know, I'm actually interested now in studying this. But this would be at least a year-long project to understand this. But thankfully, there are other ways we could repeat the experiment. Because obviously, if people really want to study this, they can. You know, there's nothing stopping humanity from exploring this question of, gee, can we redshift something going through a cloud of electrons? And kind of closer to home, we could see if there's frequency changes in the radio waves of radio signals going through the ionosphere or various parts of the atmosphere. That's another one. But then there's another thing. I think this was very telling. I'm gonna. This is a cosmological take on a laboratory experiment. It's intrinsic plasma redshifts now reproduced in the laboratory. A discussion in terms of new tired light. So this is Ashmore is the researcher, but he's citing the work of laser physicists. I'm just going to read his take on this. Recent developments in laser-induced plasma have shown the characteristic recombination lines from atoms within the plasma itself are redshifted. Importantly, the experimental results show that the redshift of these lines increases with free electron density of the plasma. Long predicted by exponents of alternative theories to the Big Bang, these intrinsic redshifts produced by plasma in the laboratory give credence to such theories. This paper gives an overview of the laboratory results of Chen et al. And relates them to predictions made previously by the new tired light theory. So this isn't the old tired light, this is new. The plasma-induced redshift, line broadening are all predicted by the new tired light. A further laboratory test is suggested whereby new tired light predicts the wavelength of the secondary radiation emitted by the plasma should new tired light be responsible for the redshift. Now, I do have to caution here. This is where the photonics and the quantum mechanics and all the electromagnetics gets just kind of nightmarish, because we're constantly, you know, in a lot of the physics literature, you're constantly switching back between kind of a quantum explanation or then a more classical explanation. You know, they call classical electrodynamics, and sometimes I think even the researchers get it mixed up, because when you try to actually do it in all quantum mechanics, it could be too difficult. And then there's something called relativistic quantum mechanics and stuff, and I haven't even touched that. But
yeah, I haven't even touched quantum mechanics.
yeah. So, well, you saw a little one here. E equals h nu. That's the beginning of it all. E equals h Planck's constant times the frequency. That's
Yeah,
the basis.
I also know what the electron hole is, and a tiny bit I know, but nothing really.
So there's a question whether it needs to be re-emitted. So the idea is the photon can hit, like, say, an atom, and then the atom will then, after it absorbs it, it'll re-emit another photon. It's a philosophical question if it's the same photon, okay, but they've shown that it's possible that this is a re-emission. I don't think anyone really knows. Now, the paper that you and I had been talking about that kind of inspired the show was where it actually doesn't re-emit. It just, the atom will absorb a little energy off the photon, and then it gets redshifted. And so the photon's still traveling along the same path. It just runs into the electron, and the electron takes a little bit of energy off of it, and then the photon keeps moving in the same direction. And
I have a question about the photon. Yeah. In the last paper, you showed like this with the sinus curve, and which is decaying. This, do you remember the image?
Yeah, I'll
Which you
show it to
wanted
you.
to?
Oh yeah,
Yes.
the decaying. Oh yeah, the one that you said you recognized, the electrical engineering.
Yes.
Okay, let me see if I could find it. Polarization, redshift. Now, I did have problems with the essay, and I need to talk. I'm actually in contact with a plasma physicist. I have to contact a few plasma physicists that I actually started to, one that I actually know, and there's a list of people I need to contact because I need to talk to them, and then they're atmospheric physicists. So in this one, I'll show you the picture you were asking.
Yes.
So this is the paper I reviewed before. I think there's some issues with it, and I need to talk to them. But the shape of the, oh, it's not this one. Hang on. I apologize here. Let me see if I could find it. This is it. Here we go. I'm pretty sure this is it. Okay, this is the paper I was reading and got to page 14, and the picture is, we're getting close.
This one.
So from a 2D perspective, it's here, but really the 3D is this one.
Yes. For me, I don't know. I don't know any quantum physics, but to me it looks like when I have a string and I flip on it, then there is a wave going along the string, and it can reflect from at the end of the string or whatever. And to me, this looks more like there is a wave somewhere in space which goes into some direction, but I don't really know. Just from this graphics alone, I don't know if I would call that a particle. Like you can make an abstract model of it as if it was a particle, but it looks like a wave. But that's just the way I see it now. And is that what is the quantum mechanical thing behind it?
Okay, so the classical electrodynamics, let me show you the classical, let me see. So pictures are worth 1,000 words. So I'll show you the classical. Light wave. So Maxwell's equation predicted these. Okay, so I'll show you the difference between the classical and the classical electrodynamics versus more the quantum. In classical electrodynamics, like when you have a flashlight on, it's a continuous wave. And so as long
I'm
as you're
familiar with that image.
right, but you see, it's just continuous. It's not little packets. The quantum view is if you have very low intensity. So what will happen is in the classical view, and go back to the classical view. So when your light intensity is stronger, the amplitudes are just bigger. That's kind of the classical view. But in the quantum view, what ends up happening is when you have more intensity, you have more of these things. So it does have the same frequency, but it comes in little packets. And so what the paper was saying is when you have high intensity light, you have so many photons just bombarding the atom or going through space that in the limit, it'll look more like this. But when you reduce the intensity, it starts to look more like that picture that you're curious about. So
Yes.
that's what they're making the distinction. They said, if you have just a few photons, it's going to look more like this.
And on a string, the mechanical wave, if they are phase shifted, then they cancel each other out. When we have a lot of light, a lot of photons going to an atom, why are they not phase shifted so that they cancel each other out? Or isn't that how it works with electromagnetical waves?
Can you say that again?
Um, when I have mechanical waves or sound waves, when I send a noise or a vibration or whatever in a specific frequency, and then I send another one which is 180 degrees shifted, then they perfectly cancel each other out. Obviously, if they are of the same intensity. But when I have, do you understand what I mean with the
y-
sound side?
yeah, actually, this is really, you're raising a tough question I don't have the answer to, but I actually had it in my control theory book of all places. You can make anti-noise, and
Yes.
you can actually send sound waves that will cancel out they do this in airplanes. If you have a good understanding, well, that's like echo
That
cancellation. If you can predict how the wave is going to behave, you just send the anti-wave, and you
noise
can,
canceling headphones work like that.
yeah. So how this can be done in the electromagnetic world, I don't know that anyone has tried. I,
Um, for me, it's just like when I have a light source which has, let's just say, the sun, and then a lot of those waves come to the, uh, uh, f- like, if I'm not mistaken, this paper was about like when the sun shines on the atmosphere, then it is blue shifted, the light, or isn't that right?
no, well, actually, that
Or
this paper was actually trying to say it's more complicated. They're actually suggesting that ultraviolet light is redshifted, and that's what you actually see is the redshifted ultraviolet light. And they gave their explanation. I don't think it's resolved. But oh, I just wanted to tell you, I just remembered there is something that uses Snell's law. There's this mirror, and so when the incident light hits, it shifts it. It makes kind of that noise canceling wave back that reflects, and it has a funny effect that it, it suddenly looks dark, I think. It's just
don't
kind of bizarre.
don't they also measure like gravity waves with that effect? Like
That's
this,
beyond me. I
um, the if I'm not mistaken, um, I think you, perhaps I'm mistaken here, but I think you mentioned the device once in a stream. Like you have a laser beam, then you send it to a mirror which splits this beam in half. Like one goes straight and the other one turns right. And then you have two mirrors there at the same distance. The light gets reflected back, and then it gets fused again. And those two light waves, if they are if the distance of the mirrors is precisely the same, they add it to each other and they get the same light intensity again. But if the distance is if the distance is slightly moved, then the obviously the laser beam gets a phase shift, and when they get added together again, then the phase shift causes the light intensity to reduce. And if the phase shift is 180 degrees, then it gets completely cancelled out. And because of that, you can measure very small distances, obviously depending on the frequency you choose. And you can do that over very large distances, like, and that way you can basically measure gravity waves. So you have like two tubes which are a few miles long with vacuum in them, and you can have detect very small distances because you choose the right frequency. And then if there is a gravity wave which comes from, for example, north to south, then this mirror moves slightly, but the other one, which is west east, this doesn't move. And then, yeah, like Mr. Yeti said, this is how they measure stretching of space time. So that's how they detected the, yeah, space time waves. And they can measure like I think if black holes fuse or like certain stars, yeah, I think black hole fusion, they can measure that way, and other very huge mass changes in space.
No, thank you for sharing that. My professor had mentioned it, and since it wasn't on the test, I didn't pay attention.
Yeah, I'm not the type who learns stuff by heart and then forgets everything after the test. I don't learn everything. I want to understand it, and when I understand it, I can remember it quite well. But if I don't understand it, then I don't.
Yeah. I have a good short-term memory, but then it's gone. Like even 3 days after the exam. You know, I've actually been in some debates, and then I'll watch it a year later. I said I said so many. You know, I was listing all these data points that I couldn't recite now. You know, I looked at some of the debates like with Dr. Dan, and I listed all these facts. It's like I'd totally forgotten all of that. I couldn't debate him again today because I'd totally forgotten what even I said. But so that's an interesting. So Mr. Jetty, thank you for your comment about if you had the right setup, you can get cancellation. You can get, oh, dumb me. That's what we call interferometers. Oh,
Yeah, I forget the name too. Like
oh
I
boy.
said, I know how I understand things, but I can't remember it. That's why I studied electrical engineering. You don't have to learn anything by heart.
Oh, now I'm embarrassed because um, uh, in the defense industry, they use interferometers all the time for various things. I don't know. I think certain missile systems want to use an interferometer, or defense systems, they want to use they use a lot of interferometry.
For
I,
sound or light?
I think radio. So
Mhm.
let me see. Oh, well, it would make sense because the shift in the radar waves, if you use an interferometer, you can measure the shift. The interferometer, that shift will then tell you the relative velocity. Yeah, yeah. See, they have this I just looked it up on Wikipedia. The interferometric synthetic aperture radar. Uh, interferometric synthetic aperture radar is a radar technique used in geodesy and remote sensing. It has applications for geophysical monitoring of natural hazards. For example, earthquakes, volcanoes, landslides, and in structural engineering, in particular monitoring of subsidence and structural stability. Okay, so now I'm really embarrassed here because you're asking me a question about the cancellation, and there's been all these devices that are just all over the place that's what they have. They won't work unless you can do something like that. Yeah. So there you go. I totally forgot about the interferometers. Oh,
Yeah.
and I forgot this. Now I'm really embarrassed. This is why it's good to talk about this, because then I remember all my physics. There's a famous interferometer in physics. It's the Michelson-Morley Interferometer, where they're trying to measure the ether and they couldn't find it.
I
And that's
think
a
you
whole
talked
other.
about that one. That was the thing I was referring to.
Oh yes, the Michelson-Morley Interferometer. Now
You
I'm gonna
said you
have,
wanted to build that one or not?
huh?
You said you wanted to build that one, or
I was building a laser interferometer. See, now I'm embarrassed because I had the parts. Um, I'll show you my laser sometime. It's just a little handheld. Um, I'm embarrassed to say this. It's probably it costs probably half as much as my old car. And I hardly ever use it. Yeah, it's an interferometer. It's a pretty good interferometer. You know, if you squeeze the light wire, you know, the optical wires, it'll detect the pressure changes. And that's probably why it's not a good interferometer to measure absolute motion, because it's too sensitive to barometric changes. And
also, Mr. Yeti said before that you need two of them to cancel the local motion of stuff. So perhaps one at your house and one at some other place,
yeah,
a mile away.
So just briefly about the Michelson-Morley Interferometer, Reginald Cahill and others have reanalyzed it and said, okay, if you have a refractive medium like air, it's better if you have something like glass. But air can actually, you might be able to, you can reinterpret the data of Michelson-Morley to indicate that they probably did detect absolute motion. And so that is an ongoing debate within kind of the alternative physics community, and I've been following it. So using the optical wires is one way to try to test this. And there has been a test in Belgium. There's an old Belgian communication company called Belgicom, and they're sending light waves through to two different cesium beam atomic clocks, and the direction of the transmission actually mattered. And they claimed that they had seen detection of absolute motion. So one way you could do it is with precise clocks, and in the absence of having cesium beam atomic clocks, you can build an interferometer. So now I'm embarrassed. I built one of these things and I forgot. See, told you I forget. Anyway, so you know, I think we had a good show, and we were talking about this here. So I'm just going to complete the thought. What they're saying then is, when this packet here, so you know that the radio wave has a big wavelength, and they estimate that the height of the photon is on the order of magnitude of the wavelength. So, you know, if you have like a meter long wavelength for a radio wave, that the height, this height here, the maximum height would be on the order of about a meter, and then it would be several meters before you get to the tail. So it's different when you have the continuous pulses. So like when we're measuring this, like on the oscilloscope, it looks like continuous. The carrier wave will be continuous. But if the carrier wave is weak enough and you have a good enough oscilloscope, they're claiming you should see something like this. That's what quantum theory would predict. And it's when you have very sparse things, that's when you can get very interesting interactions with the electrons, where the electron can then start to cause the redshift. I'm not saying that this is correct, but that was the basis of the paper. That you need weak starlight, and then the electron, a free electron plasma, it's going to behave differently. So this is where it gets a little funny, where we're modeling. You know, we do a lot of our electrical engineering with classical electrodynamics. You know, a lot of the radio engineering, at least, and audio engineering, we're not thinking about individual photons. In this case, it might matter. So that's why I'm very interested in pursuing this, because that could explain then the redshift we're seeing. And I'm even heartened by the fact that there's a correlation between the polarization and the redshift. That seems to be a plasma influence. But you know, this is so early on, and before I commit to studying this more, and I wrote you that I'm interested in studying photonics, I think I want to have conversations with some plasma physicists first, and so some photonics physicists. So You're going into this just because it's very interesting to you. I have, I have my reasons that are related to, my study of origins and the Big Bang.
Yeah, it is for me, it is degree I'm interested in, and not one which is benefit. And I didn't do it because it is beneficial for my career, even though it is. But there were, if I could study whatever I want, I would probably add a few others as well. But at some
Yeah.
point, I need to think about like um, having a more consistent life.
Oh, I'm the same way. And how I ended up in biology was just kind of economic need. Dr. Sanford just kind of pulled me off the street, so to speak. He said, "You have the right skill set." And I said, "I don't have any biology." He said, "You'll learn it." And so I had a major, you know, detour in my professional development. Although I'm very glad to have studied biology, it's been a lot of fun. But now I'm kind of going back to this is why it's been kind of a fun couple of weeks, because I'm going back to my physics and electrical engineering roots, and the field has changed a lot. Like I never heard about this. So you have photonics, and then I have the polaritonics, which is really incredible. So now these electrical engineers are now dealing with other kinds of quasi particles to make their next generation devices. That's all new to me.
Yeah, but for example, I studied at this university, and it was like, yeah, total Swiss-wide, it's like around 6,000 people who study there. But at my place, it's less. And the electrical engineering course, it's like per year, it's around 70, so it's not that many. Um, so the advantage that it was way more personal. So the teacher knew our names and stuff like this. But I studied there, and during the time I studied there, there was the photonics course all along, and I've never even heard of it before. And only after I went only after I left that school and worked for a while and looked at what I could do a master in, I saw photonics, and then I looked which school does offer photonics, and I see like the one I attended. And
Yeah.
I was very surprised, like, what? How long is that there? And it's like 10 years. And I was like, okay, never heard of it before.
Come to think of it, when I graduated from George Mason in electrical engineering, they didn't have, I don't recall any photonics courses. It just
Wow.
depends on what skills your professor has.
Yeah, I
Um,
didn't know. I didn't hear of it either, but it was there. I just missed it. And it was like the building next to me, and the buildings aren't that huge. So, yeah, it's just
yeah,
you talk to certain people and you know them, but there are others which are your neighbors, and you never even notice that they are there. That was the case for me.
and there is a society. Um, my boss is a member of this society. I think the name is French. So the acronym is something to do with photonics. So that'd be really neat if you end up joining the society at some time. The International Society for Optics and Photonics. Uh, it's called SPIE, which is an acronym for the French, for a French word, I think. So that'd be really great. Um, so that was my closest, because I had worked on, if you do computers, then you get to do lots of different jobs, because a lot of departments want a programmer. So that's how I bumped around to different projects, from like telephones. And then I got into one at the Army Night Vision Labs here in the United States at Fort Belvoir. And they use a lot of photonics because of the night vision
Yeah.
devices that they have and cameras. And so my boss was a member of the SPIE. And so that was my closest involvement with photonics, but I was just doing the processing of the of the images. I actually didn't build the photonic devices.
Yeah, for me, it's I will most likely go into the firmware or embedded area when it comes to lasers because that's my work experience and my interest. And so I won't be the like with the powerful computers, but with the small microcontrollers, which are
Yeah.
very close to the physics. At least that's my speculation. It's very hard to predict the future, but yeah, that's would be my focus. And yeah,
Well, that echoes. Guess what I was working on? I wasn't working on the firmware, but the embedded system.
yeah.
They had various kinds of codes and operating systems. Um,
I normally
I don't.
work below operating system level.
Wow!
Not
Wow!
it's just the controllers are too small to be able to run operating system. They are able to run like RTOS, like real-time operating system with a few kilobytes, but not the very stripped down Linux with a few megabytes. So yeah,
Well, you know what this suggests to me is that either it's meant to be very cheap or very, very fast, or very
yes.
compact. That they don't, um, you know, with embedded systems, is very dedicated. And boy,
It's not
that's
only it's not only about cheap or fast. It's more about like little energy and little heat.
ah.
Um, and obviously less weight because cooler or whatever. So it's like small, little energy, little heat. That's the point. And when it comes to lasers, um, like the school I'm going to, they are focusing on like the pulsed lasers. So if you want to control them, not just turn them on or off, but to have a control system, then normally it's faster than any microcontroller can handle it, or like on the
Oh,
limits of it. So yeah. And how I could program them, at the company I'm working at the moment, we use C and do object oriented C. So like we invented it our own object orientation thing, which made it pretty tough to get into as well. As,
yeah, that's how we did it. It's like, uh, we would actually just, like, I guess, program the memory areas and say, okay, just put this here. Um,
how
it
did you
was
do it with? Also with C, or what did you use? What programming
we used
language?
C, because C could actually, you could say, okay, um, you use C to be able to, just so you have kind of like a, some sort of human language like thing, because you don't
Yeah.
want to be talking in terms of bits and bytes or hexadecimal. But then you could actually, like, at least simulate it on your, you could write a C program, and then you simulate what the microcontroller's behavior would be,
Mhm.
and then you could just kind of, um, it'd be nice, you can kind of test how this is going to behave.
We do our testing on microcontrollers, and but on test setup microcontrollers with easy access to the pins. And we have another microcontroller which is the tester, and then all the outputs and inputs are simulated from the tester side. And so we do it like this. We don't virtually simulate the software. We
Yeah.
always compile it and put it onto the microcontroller and build a test setup around it.
Oh, yeah, that's right. See, it's been so long, but there has to be like some sort of compiling process where, maybe some stuff that you don't always need to directly program. Um, you're going to have to throw it into like the embedded system anyway, but then all the things you really are, you know, that you really want to adjust, that's where you have to think. So
In
yeah,
when it comes to programming, uh, certain high-level programming languages are compiled to C, and then or perhaps that step is skipped. But then from C or the other equivalent, it is compiled to assembler, and then that is assembler is also very closely related to the instruction list, which is in the language of the microcontroller. And as for we have a debugger, and this debugger can basically look at whatever the code is doing on the microcontroller, and it's a very buggy debugger. Sometimes it just doesn't work, and then you you try a day, and then afterwards, then you find out that when you do exactly the same again, then it works and stuff like this. But normally it works, just not always. And there there is a mixed mode where you see the C code, and then in gray the assembler code, and then so you see basically what the optimization of the compiler created, and that sometimes helps a bit. But yeah, optimization in the compiler is always weird. So if we try to debug, we try to disable the optimization.
yeah. So before we finish up, I just wanted I had oh yeah, one other thought is will you when you're working with the lasers, will you actually be trying to design new lasers or its properties? Or are you going to be? Do you know what kind of lasers you might be working with? Like, would they be like these these diode lasers or gas lasers or high powered? Or are they communication lasers?
I think it's just diode lasers, but I haven't. I
Okay.
just had a tour through through the facility, and for I don't know an hour or so. So um, I didn't pick up everything, especially names and stuff like this. I'm a bit bad at, so I don't know what specific laser and everything. But
Yeah. Yeah.
yeah, so I will know more when I work there.
Yeah. You know, there's diode lasers are just incredible. So they have a variety of, I'm sure they have a variety of applications for like diagnostics. I know lasers are used a lot in biology to, you know, like we're looking into the genome, the way we can, some of the gene sequencers, they use laser technology. It does something to the DNA to help us do the sequencing, the chemical sequencing, but you need there's like all these automated gene sequencers and the laser is important to kind of help do the photographic work that's kind of fed into the computer and it does this gene sequencing. I don't know exactly how it works, but it's going to be all over the place. So anyway, if you had,
I think the lasers are relatively normal ones in, I don't know anymore, 100 watts or something like this. Is that normal? Or 100 milliwatts? I don't know. But yeah, it's normal range. It's just that they are pulsed in, I think, femtoseconds. So the average power output is normal, but the individual pulses are very high, and the frequencies are around about the visual range. I don't know if it's infrared or whatever, but it's not like far away. So
yeah,
that's about everything I remember.
well, you asked about before we say goodbye. You asked about variable speed of light. Would you be? Uh, you're welcome to come on my show on Saturday, and we could talk about it.
Yes,
That's
I can. I
okay.
have time then. Mhm.
All right. Well, we can just we know at least now that we can connect, and it's just kind of nice to just hang out with friends.
Yes.
Um, this is these are the sort of things we like to talk about, and I yeah, it might be a good time to talk about all the various young Earth creationist cosmologies for variable speed of light, and then also the secular cosmologies. So, all right, if you had,
Mhm.
I'll give you the last word, and then we can shut the stream down. I'd like to thank everyone that's joined us in the live and also by recording. So Ben Rex, if you have anything you'd like to share with the audience.
I want to thank you for the work you're doing and the audience for being civil and nice and all smart people. Yeah, thank you.
And thank you, Ben Rex. I'll see you briefly in the backstage. So I'm just going to end the stream and then I'll meet you there just to say goodbye. And Paleologos is here. Greetings. We were just nerding out here. So anyway, take care, everyone, and the grace of the Lord Jesus Christ.